How do we represent all these zeros and ones? Yes? How I added, like, in the binary? Yeah, so Francis, right? Yeah. So in this case, the simplest one is 0 plus 0 is 0, right? The second simplest is 1 plus 0. Actually, this is a carry, so it doesn't count. Do we have a simple one? Yeah, 0 plus 1 is 1, right? And if we had 1 plus 0, it would also be 1. So that's not too difficult, right? That's no carry. That's like what we have here, 7 plus 1 is 8. Where it gets difficult is if we add a 1 and a 1. Then we have to take 0, carry 1, right? Because 1 plus 1 is 2. 2 is 1, 0. So 1 in the 2's place, 0 in the 1's place. So we stick the 0 down here, and we carry the 1. So we could write a little 1 up here. And the 0 plus 1 is 1, but add that 1, we get 0, carry 1 again. And then we add that to 0, so we get 1, 0. Making sense? Any other questions? Right, so how do we do this in a computer? Well, we represent these numbers with wires. Can't really see the coloring here, but some of these wires would be 0, some would be 1, and that would represent these numbers we see here. In a circuit schematic, we write this as /8 because writing 8 wires is kind of cumbersome. How do we add? So this is a basic adder circuit. It's a little bit complicated to understand. You don't need to really understand it all, but to give you a basic idea, we start out by taking our first digit from one number, our first digit from the second, so we have two 3-digit numbers coming in. We take the first number from each. This is an XOR gate. So it basically returns a 1 if either one or the other is 1, 0 if it's neither or both. And we can implement that using our other basic gates by basically saying it has to be either, or it has to be or and not both. And both would be and, right? Makes sense? So we can make an XOR gate as a compound. And that gives us, if we go back, 1 plus 1 is 0. 0 plus 1, actually this carries so it doesn't work well, but 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0, right? So that's exactly what the XOR does, and that's what we use. We only carry if we add a 1 and a 1. So we get our carry bit, oops, wrong way, by ANDing the two. If they're both 1, then we carry 1, right? And that gives our first digit of our output, which is a 4-bit number. This next bit is the same as the first, except it has to deal with that carry, right? So we have the exact same idea of take the second bit, XOR it, and AND it. But if we carry 1, then a 1 turns to a 0 turns to a 1, right? Because a 1 carry 1 gets 0, and then we carry that other 1, and a 0 carry 1 just becomes a 1. And then that we send out to our output, and calculating the carry of this, we have to take, is it originally supposed to be carry? If yes, then we're good. If no, it could also have to carry if we get a 1 here and a 1 carried in. That make sense? So that carry then we pass on to the next digit. And we can stick as many of these as we want to add 8-digit numbers, 16-digit. And digit in binary is also an 8 or 16-bit number. Now we can get into a little bit of memory. So that's how a circuit will add numbers. Memory is how circuits remember things, right? So circuits are just wires. Wires, if you turn them off, they're off, right? Doesn't work so well. But we can actually hook up these gates in a really clever way. This is what's called an RS latch. So now this is difficult to understand, so try to bear with me here. Think really hard about it. Assume for a second that this is off, this is off, this is off. So what happens? 0 comes in here. Well, this is off, so that's a given. So we get this 0 coming around here. This is off. 0 or 0 is? Pardon? So just yell it out. 0 or 0? 0. Yeah, right? They're both 0. So we get a 0 here. Not 0 is? 1. We send this 1 up to here. 1 or 0 is 1. And then we not this 1, and we get? Right, and that completes the cycle. So with everything 0, assuming this starts at 0, we have a 0. Now what happens if we put a 1 on this S? So we initially had 0, 0 coming in, but now we're putting a 1 on here, so 0 or 1 is 1, right? And initially, this 1 coming out is because this is 1. And not 1 is? And this 0 comes up here. This is also 0. 0 or 0 is 0. And not 0 is 1. This 1 comes down here, and now it's being put into this gate. That keeps this gate at a 1 even after we turn this off. Cool, eh? So now that we've put this on for an instant, this is now a 1. If we put this one on, then it suddenly does the opposite, right? Because this is coming in as 0, it inverts that, gets a 1. Then we stick a 1 here, inverts that, gets a 0. This gets a 0, this no longer keeps this one on, we get a 0 again. So this stands for set. Set means put it up to a 1. Reset. Reset means reset it to a 0. A lot of logic there. Making sense? So that's the basics of how computer memory works. We can then put a bunch of these into a box and wire them together and stick in an 8-bit data in, 8-bit data out, and make what's called a register. A register basically remembers 1 bit. A register can remember an 8-bit number by just remembering the bits separately. So a register then is the very basis for computer memory. Computer memory, we just take a bunch of these registers and make them as big as we want. Any questions so far? So now we can get into the last little component we'll look at, which is multiplexers. So a multiplexer, its schematic is this. And what it does is, if this is a 1, we're going to take Y and send it to the output. If this is a 0, we're going to take X and send it to the output, right? How we implement that is with a couple gates. So if this is a 1, then we're going to stick this 1 into here, and a 1 and anything is that thing itself, right? 1 and 1 is 1. 1 and 0 is 0. So 1 and anything is that thing. 0 and anything is 0, right? So this thing or 0 gives us this thing. If we stick a 0 in here, now we have 0 and Y. 0 and Y is 0, right? Because an and has to have both as 1. And then we invert it, and we get a 1. 1 and X is X. So we have X coming into this OR. We have 0 coming into this OR. 0 or X is X. So we can use these gates to select X or Y. Make sense? And then we can combine them and make compound multiplexers. So multiplexer, I don't know if I said, is the name of that thing. We take 2 of these, and we basically just take a multi-bit line and put 1 to 1, and put the select to both of them, and send both outputs to another multi-bit line. Make sense? And the last thing we can do is we can combine them in a different way to select between 4. So this time we have a multi-bit selector. The first one goes to this set of multiplexers. Second one goes to this one. So this one says, take either 1 and 3 or 2 and 4. And the second one says, take the one from this or from that, right? So if we put a 0, 0, we're going to take this one, and this one, and then the one from this one, so we get the first one. 0, 1 gives us this one, and then the first one, so we get this one. 1, 0 gives us this one by the same logic. 1, 1 gives us this one. So 0, 1, 2, 3 gives us 0, 1, 2, 3. Kind of cool, eh? And we can expand that. We can do the same logic, except with 3 of these big ones to make it select between 8. Any questions? I'm seeing a couple confused looks. You don't have to understand this fully because we're not going to be building circuits in this course, but so that you have an idea how these darn computers work. So now we can get out into what a computer actually does. So we know how we can select between a bunch of inputs. We know how we can make multiple inputs. how we can memorize numbers, and how we can add numbers. How does the computer actually use those circuits? So it uses them by using commands. So we have, say, a command that will add these three values. So CX, AX, and BX, you could think of them as a variable. Anyone have any idea what kind of component would represent that variable? So we kind of learned three. We learned adders, we learned multiplexers, we learned registers. Which one would be a variable? Pardon?
Registers?
Yeah, registers. Remind me your name?
Kelvin.
Kelvin. That's like the third time you told me. I'll remember it next time. Yeah, so a register remembers these three values. So this is saying add AX plus BX stored in CX, right? And we use our adder circuit to do that adding, and the registers to store. Move BX to 2 just changes the value of the register to 2, right? Those are basic computer commands. So yeah, we use the adder circuits, and we have what's called an opcode. The opcode basically says, which command are we doing? Is it an add? Is it a move? Is it something else? So we can set, say 0010 is add, 0011 is set equal. And we also have binary values that represent each register. So we can have 0, 0, 1, and 1, 0, right? So set AX, or CX equals to AX plus BX would be, this is our set, right? So this is our add. So 0010, 10 is CX, 00 is AX, 01 is BX. So CX equals AX plus BX, and there's the add. Right? For the move, we do a similar thing. We have our opcode, we have our value for the register, and here, instead of our two registers, we have our constant value 2. Right? 0010 is 2. That's an example of a very simple 4-bit computer, because it handles 4-bit constants. Right? So if I wanted to set AX equal to AX plus BX, what binary code would I put here? Sarah, I've heard from you a lot. Let's see if someone else can get it. Yes. Sorry? Oh yeah. So if I want to set AX to AX plus BX, so we have 0010 is add, 0011 is set equal to, and our registers are represented thusly. Okay, so let's break it down. Oh yeah, do you have an idea? Yeah, right? 0010 is add. 00 is AX, 00 is AX, and 01 is BX. So AX equals AX plus BX. Make sense? So that is our machine code, right? These values here, these are represented directly in the memory, and our computer's main memory is just a bunch of registers. Oops. And that contains these instructions. So how does the computer go through this main memory and evaluate those instructions? That's what a CPU does. So this looks kind of complicated, doesn't it? Right? But it's all stuff we know about. It's a couple registers, a couple multiplexers, a couple adders, other things that we can put anything in, and a couple gates. So let's go through what it does. So we start with our code to execute. And we have 4 registers. So we have AX, BX, and CX. We'll get to this in a bit. Okay? So let's look at what we have here. This is our set, 0011. And then 01 is BX, I think. Maybe it's CX, I forget. And 0010 is 2, right? That's a constant value. So let's look at which register we're actually setting. So we'll start with the opcode. So the opcode is 0011. We send that into this big multiplexer here. Right now it's only selecting from 4 different values. We can see it has 4 bits of input. Anyone have an idea how many values 4 bits of input can select between? Yeah, I heard 16, right? Because 4 bits gets us 16 different values. Since we have 2 to the power of 4 is 16. So we could potentially have 16 different opcodes. Right now we just have 4. And those output values come all the way from these 4 circuits right here. So our opcode says, which of these 4 circuits outputs are we actually going to use? And then we stick that into these wires here. These gates decode this value. So they're what's called a decoder, and what they do is they turn 0, 0 into a 1 on the AX line and a 0 everywhere else, 0, 1 into a 1 on the BX line, 0 everywhere else, and so on, right? So you can kind of see how they do that. If both are 0, or sorry, both are 1, it'll put 1 onto the IP line. If both are 0, so not, and then AND them, put 1 onto the X line, and we not one or the other to get B or CX, okay? So that says then, we put this into write enable. That's another input to a register. Basically, it puts an AND gate in front of everything. Yes, Sarah. Sorry, yes. I will try to talk a bit louder. So write enable puts an AND gate in front of all of our register latches. So if we have a 0 on that, that means that neither the set nor the reset is going to be a 1, and it can't write to that latch, right? If it's a 1, then it bypasses that AND gate, and we pass the same value through, and we can write to it. So we're changing the write enable for just to be 1 on just one of these based on this value. Make sense? So we take the output based on the opcode, we put it into the register based on this identifier. But how do we calculate the output? So we have the adder circuit, we can have some other circuit, could be a subtractor, a multiplier, whatever we want to put in there, and it can take its input. So its input is that last little bit we have to handle. So we have 2 possibilities. One is that it could be a constant, right? If it's a constant, we take these 4 bits and we send them directly in a 4-bit line to our constant value circuits. So move just sets. It doesn't do any computation. So we send this 4-bit constant, it just goes right through, all the way around to this multiplexer, and it moves 2 into BX, right? If we happen to want to use 2 registers, then instead what we're going to do is send these 2 bits to this multiplexer, these 2 bits to this multiplexer. It'll select which register we're going to take the input from, and we're going to send that input to this adder circuit, for instance, that'll take the input from 2 registers and stick out the sum, right? So when we add AX plus AX, we're going to take the multiplexer, or sorry, add AX plus BX. This multiplexer here is going to select for AX and send it up here to the adder. This one's going to select BX, send it up here to the adder, and that'll add the 2. Send it around here through the multiplexer, put it in, this will select for it, and it'll store it in AX. Whew. And that's how a CPU works. Any questions? So, there should be 2 questions you might be asking yourself. Any idea? Yes? So, like, what numbers do you get where? Okay, so you get, it depends on what instruction you just ran. So if we just ran set bx equal to 2, then it's going to send this to through the move all around here. It's going to select for the move, and bx is going to store 2. The others are going to remain unchanged, right? And depending on what else we do, if we do an add, it'll just change the 1 register specified here. The others will not change. So the 2 questions I was kind of hoping you guys would touch upon are 1, what's IP used for? And 2, where does this number come from? Right? So we're going to touch on that now. We add, so if you guys can't see what we just added, look here, we add this little +1 circuit and our main memory off to the side. So we'll start with our main memory. That's where this number comes from. It's 10 bits, so 16 different 10-bit registers. And it sends this 10 bits over a 10-bit line, puts it in here. This box isn't anything fancy. It's just a wire that connects this 10-bit line to this 10-bit line. Okay? This box just kind of shows it so we can see it nicely. This main memory here is a bunch of different 10-bit numbers. So one of them could be this. One of them could be adding. One of them could be doing something else. And it is selected based on this multiplexer here. It says take one of these and send it to here and run that command. How do we know which one to run? That's where IP comes in. So you'll note that The selector for this, 16 bits, or 16 different values, it's a 4-bit line, and it comes from IP. So IP stands for instruction pointer. It's a value from 0 to 15, so 16 possibilities, and says which of these instructions we're going to run. It is a little bit special, because if we don't specifically change IP, if we say set bx to 2, and that's, say, right here, and then we're going to set bx to 2 again, then we're going to set bx to 2 again. That's not going to do anything useful. What we want to do is add 1 to IP so we can move to the next instruction. And we do that by taking IP, sending it through this +1 circuit. It's like an adder, except one of the inputs we just hardwire to a 1, and that's going to send it back into IP. We might also have an instruction that lets us set it explicitly. So say go to 0. Go to the beginning of the program. In that case, that instruction would have a special opcode. That opcode would be recognized in this multiplexer here, and it would say instead, take the value from the input that we got, where is it? Right over here, from the output of this circuit that came from the opcode that we just ran to change IP. That's kind of a lot to take in. Does that kind of make sense? So that's how we do basic program flow. We run command, 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 jump back up here. And then we can do that until we're done. Right? So that's sort of putting everything together, a very basic CPU. This would almost work. The one thing we're missing is clocking. And that's where we basically put on these registers a clock that says only update once every, say, 50 milliseconds. And that controls it in terms of timing, because we want to do this all at once and then do it all at once again. If one part of the circuit's doing one command, the other is doing the other, it's going to mess up. That's a little bit more complicated to understand, but the basics is all here. And in fact, if we made this main memory a little bit slower, this circuit we see right here would work. That's what a CPU schematic looks like. And that's what's inside all the computers you're using here. Any questions?